Hello, good morning to everyone. I'm sorry that I cannot speak your beautiful language, so I have to stick with English. So hope my slides are clear enough to promote the message that I have. My background is from grease industry. Since 10 years ago, I'm working for NYNAS. They're one of the largest naphthenic oil supplier on the global basis. And my passion, but still, is grease. So what is about today? Today we are going to talk about using naphthenic oil, high viscous naphthenic oil in number of greases and evaluate the performance of those. We know that high viscous products are used for mining, for heavy load applications, open gears, but also in many cases it could be blended with paraffinic group 1, 2, 3 and make so-called multi-purpose greases. All right. This is the outline of my presentation, so I will just give you a slide on what we are doing in our company and how we support customers. Then I will move to the challenge within the grease industry. Some experimental work, and at the end, after experimental work, I would like to introduce you with 1 or 2 slides what I call increased productivity index, how it is possible to increase production within the same process line, within the same manpower, by selecting the right oil. It sounds like magic, but I think it is possible. And at the end, summary. I'm not going to go through this slide. This slide demonstrates some of, not all the applications that we are supporting. So we have process oils, tires, transformer oil. I think we are, I'm sure that we are world leader when it comes to transformer oil worldwide speaking. And the last part is the base oil, where I am, I would like to say I'm in charge, but I'm not in charge. I'm just working within this group. So we are supporting not only lubricating grease application, but also metal working fluid and hydraulic gears or gear oils and so on. All right. We know that according to American Petroleum Institute, the base oils have been classified in 5 categories. The first 3 are dedicated to paraffinic oil, group 1, 2, 3. The differences between these 3 are, according to this slide, is viscosity index, sulfur content, and saturation, degree of saturation. But in fact, there are more differences. For instance, degree of solvency, which is not mentioned in this kind of slide. Nevertheless, we can discuss it in separated forum, but it is extremely important for industrial applications as well as greases. Then we have polyalpha-olefin, which belongs to group 4. And the last category, group 5, is a kind of mishmash of everything. These oils have nothing in common, in fact. So naphthenic oil, according to this classification, belongs to category 5. And a slide about solvency. Why we talk about the importance of solvency, regardless if you are working with additives or greases or metal working fluid, and so on and so on. Solvency is simply can be defined as the ability to solvate other molecules. Annealing point is a good indication of the degree of solvency. So when you look at the product data sheet, you can follow you can look at the annealing point, and if it is the lower, the better. So the lower the annealing point, the higher solvency. Right. This is an example of how solvency can affect the solution of other molecules. This is a case from glue industry. We got a task from a glue industry from a customer to compare a paraffinic with a naphthenic oil, same viscosity, and melt or dissolve a certain percentage of a component. So this is we started to mix it, The melting point was at 120. We see at this stage that everything has been melted, but as soon as we go back to ambient temperature, we see separation in the paraffinic oil. The reason is lack of sufficient solvency for this case. All right, now let's move to greases. In fact, the landscape of base oil industry by application can be demonstrated by this chart or this slide. And as you can see, grease is only 3% of the total base oil consumption. However, grease is I would say, the most underestimated component within the industry. We talk about the electrification age. We talk about the battery-driven cars. In fact, in battery-driven cars, the amount of the grease that is going to be used is going to be much more than it is today, more or less double as much. So twice as much grease that is used in a modern car will be used in a battery-driven car. So this is the survey that was published for about 1.5 months ago, or less than 2 months ago, by NLGI organization, at which I had the presentation. So the data is quite fresh. And as you can see, lithium conventional lithium and lithium complex grease together is about 75% of the total production, worldwide speaking. And then we can move to the calcium type of greases is about 11%. Here, even calcium sulfonate is included. Then we move to polyurea. Polyurea, it should be here, that it has been disappeared due to the computer, I suppose. But here, this piece of cake belongs to polyurea. Is about 6%, the average production on the global basis. However, if you move to Japan, this number is closer to 30%, while in India is almost zero. So the reason that I show this chart, not only to inform you about the type of the greases by thickener that are used and the percentage that are used today worldwide, but also to highlight the fact that 75% of all greases is based on lithium metal. Lithium grease was invented in 1942. The patent is from 1942. Lithium complex grease patented 1947. But still we are using the same technology. We use the same grease, but with more advanced additives, as for instance our dear friend from Lanxess introduced to us, put into the modern car, and it functions perfectly. But the grease industry, unfortunately, has not moved on, and they don't want to move on for many reasons. So if you look at the production in metric tons, this is the yellow line indicates the production for lithium complex. For the lithium grease, so here we see a slight increase. For the lithium for lithium complex grease. For the lithium grease, we see a slight decrease. But the total, the red line, more or less indicates a very stable production over the last years. I mentioned battery industry. I mentioned electrification age. Here is a slide from Lubgrax Greases published in April. It shows, in fact, the demand, the price increase of lithium ion from 1998 to 2016. And here, lately, we see a quantum jump on the price. And this is due to the needs from battery industry. And the estimation is that it will accelerate much more. I learned that when I was studying at the university, everything could extrapolate it in a linear way, in a linear manner. But today we are living in a digital world, and everything is developed in an accelerated way. So everything is going much, much faster than we can even imagine. So here I would say even this is a very conservative estimation. So what is the message here? The message here is that grease manufacturers are going to be under high pressure. The technology is there, they don't want to move on, and we cannot change the mentality of this business, because we have the end users, they don't want to try new things. We have manufacturers who are more or less happy to have happy customers. So the bottom line is that they have to pay higher price. The competitiveness in this industry will increase sharply. I was Googling and find some numbers which might be of your interest, I felt, and that's why I put this slide. These are the top countries when it comes to the lithium production. In fact, Brazil is not too bad. It's on the seventh place rank. So today, Australia is leading, and Brazil is on the 7. But Brazil has a reserve of 48, identified reserve of 48,000 metric tons. So there are some good news still for your country that you can contribute more. So we at NYNAS, we are following this trend, what's happening. I'm not going to go through this slide. This type of information is published frequently in our magazines and is available for our readers. Oh, sorry. Okay, now we are moving to our, in fact, now I have spent almost 10 minutes of my time to go through this. Okay, thank you. Through the background and some challenges. And sometimes we ask, why not more calcium sulfonate? I developed calcium sulfonate, over-base calcium sulfonate complex, 2003 maybe. Calcium sulfonate was in fact invented by Whitco, by a gentleman, Muir, in the beginning of 1983. He has 4 patents. So, and then Chemtura, and then Total, and they followed. Most of those patents, of course, have been expired, and the information provided by the suppliers of the calcium sulfonate and additive suppliers are available, so it's easy to make it. But again, the conservatism is much often is a big challenge within this industry. So a typical multi-purpose grease consists of 10% thickener, lithium thickener. We talk about the conventional lithium grease, about 3% additives, and the rest is mineral oil. And in this case, mineral oil, you can read paraffinic group 1 oil. I visited customers, for instance, in Russia. They use 17% soap. Also, some other manufacturers, they use maybe 8.5%. So 10% is a good and gentle number for the soap. Of course, for those of you who are not aware about what NLGI number is that we measure the consistency of the product, and then we put them in according to this table. If the consistency is, or the penetration number is between 265 and 95, we classified it as grade 2, which is the most common product worldwide speaking. And this is the consistency that we were aiming when we were developing our products. Okay, high viscous naphthenic oils can be used in a number of applications, of course, but when it comes to greases and metal working fluid and so on, so we can follow a Streiberg curve. A Streiberg curve was invented in the beginning of 1903, I think. So, but it is still going strong at the university, at the tribological courses. You will learn about this. And what is interesting with this is that we can simulate more or less all the applications where we have 2 metal surfaces in contact with each other or moving towards each other or apart from each other, so we can position it in this chart. So for instance, metal working fluid is working within this area. The first one, the region 1, is the boundary lubrication, where we have lots of metal-metal contact. In this area, mainly EP additive and anti-wear has to be used, otherwise the wear will be severe. And then you have metal working fluid, which is operating in the mixed lubrication zone. Greases in a ball bearing operates in this between 3 and 4. If you look at the, for instance, piston ring, it operates within the entire region. So, when it comes to greases and high viscous products, so high viscous products simply can be used within entire this chart, this graph. But when it comes to the high viscous products, so we can see that it brings number of good properties, or offer number of good properties to the grease. For instance, it can stand shock loads. It can reduce the thickening content in greases, increase productivity, which I'm going to talk about a bit later, improve water resistance, and so on. All right. This is a slide from the first slide. I think it was 2014, yeah. I presented and where we blended high viscous naphthenic oil with group 1, 2, 3, and then we evaluated. I'm not going to go through this presentation, of course. I just want to highlight that we did our homework. Typically, as I said, naphthenic oil, high viscous naphthenic oil is blended with paraffinic oil, and this has been done. Now we are moving on, and we are trying to use high viscous naphthenic oil only to see how it performs. So for this reason, we use two different naphthenic oils, one reference oil with a viscosity of 375, and one almost with 620, 60% high viscosity. The pour point of the reference oil is better due to the lower viscosity. It's not a surprise to us. The interesting is the analytic point, the solvency, and the viscosity gravity constant. These two parameters are indicating the solvency of an oil. And here we see that the thicker product has better solvency, and it is not really usual, because when you increase the viscosity of a certain category of oil, you lose solvency. You can, for instance, compare SN500 with Bristow. SN500 has, paraffinic SN500 has a better solvency than Bristow, and so on. But here we go the opposite direction. Okay, so what we did was making conventional lithium complex, and also bentonite grease. When it comes to characterization, so we did this characterization, so penetration, consistency, dropping point, oil separation, copper corrosion, and these products do not contain any additives, so because the target was to evaluate the performance of the base oils. All right, let's see if I can make it easier to read off. So as we can see, first of all, in all cases, we have minimized the soap content. We talk about the pressure on the lithium, and here we see that by using high viscous naphthenic oil, it is possible to minimize the soap content. However, if you look at, for instance, grease B, which is based on T600, we see that the soap content is really, really low, 4.6% almost. And this is fantastic. Oh, sorry. And the other part is that when you reduce the soap content, there is a risk that your grease collapses. The shear stability will be high. Will be low. And here we see that despite of low thickener content, but the shear stability is quite well identified. The other part is that when you reduce the soap content, oil separation will increase, because the soap content is the guarantee to keep the oil inside the structure. Here we see that in the case of T600, although we reduce the soap compared with T400, but the oil separation is still remained low. Many of common specifications for lithium and lithium complex greases require an oil separation according to this method a week at 40 degrees C, 5%. And we see that the T600 fulfill all, this requirement. So what is the reason behind? The reason behind is very simple: better solvency and high viscosity. So by having better solvency, so we can get a bigger fiber, more dense fiber, and by having high viscosity, so the product will flows slowly through the structure, and thereby we get lower oil separation. The other part is flow pressure. Flow pressure is a good way to simulate pumpability. And as we can see here, we measure at -20, and the flow pressure of reference oil-based greases are better, almost 50% lower than the thicker product. And again, it is not a surprise, because the viscosity is 60% lower. However, all the flow pressure data that are measured here are more than approved, more than good enough. So they are extremely good. Because in these naphthenic oils, we don't have any wax. Typically, when you drop the temperature, wax starts to crystallize and contribute with a higher elasticity, and thereby resulting to high pressure requirement when it comes to pumpability. But here we see that the flow pressure is more or less directly related to the viscosity of the oil. The other part, in fact, in this study is water washout. We see here that in order to pass water washout, which is often 5%, you have to add a small amount of polymer. Here we see that without having any polymer, all products are performing extremely well. Last and very interesting part is the 4-ball. This 4-ball test is a severe test. We run it at 1 hour at 40 kg. And here we see that without having any single drop of additive, we are ending up with nice results. For instance, in this case, in the lithium case, we end up with 0.5 millimeter in a scar, which is really excellent. Of course, this can be improved if you wish, if someone has a tougher requirement, but I believe that all these data are really, really good enough to just get approval from a customer. If you wish to add a small amount of antioxidant, that's fine to me, but it's not necessary for a multi-purpose grease to improve it further if it's not a demand. Rheological measurement, I'm not going to go through this. I promised Joel, or I mentioned to Joel that I want to have always a rheological curve here to highlight how important the rheology is. Rheology is a science of the formation and flow. And what we are doing here is that measuring the shear stability of the product. This part, linear viscosity region, indicates the shear stability of the product. But it's also important if you are going to measure the mobility of the product in the next test, your strain which you pick up is within this window. This means that your product has not been sheared down. So that's why we take the strain here, and then we move to the next test and we run it at constant strain. By the way, here G prime is, as you can read here, is elastic modulus, representing the elastic part of the grease. G double prime viscous modulus, the viscous part or viscous behavior of the grease. And G double prime, as you can see here, is the sum of these two. So the reason that I put G double prime is that, G star is that I'm going to use it here. What we see here is that we lock the strain and then we start to oscillate it gently. And at the same time, we drop the temperature. What we see here as 25 degrees C, at which we measure the consistency of the grease, both of the G star is the same. But as soon as we start to drop the temperature, we see that one grease, which is based on high viscous product, gets more elastic or gets thicker, which is also in line with the flow pressure that we measured and showed earlier. Then we went to university. SRV machine is a very sophisticated and an expensive piece of apparatus. It's quite big. And we don't have it at our site. So we went to university and measured the friction coefficient and wear and so on for not only the greases, but also for the oils at 40 degrees C, because at 40 degrees C, we can identify the viscosity of the oil and use it as a reference when it comes to performance. So the running time was 60 minutes. We use oscillatory operation or manner. As you can see here, there is, hopefully you can see, there is a ball here and a plate here. And here you can drop, you can have a drop of oil, and then you oscillate it gently with the frequency of 50 hertz. what you get out is friction coefficient and the wear on the both on the ball, but as well as on the plate. You remember this slide? So our operation took place in this area where we had the toughest area when it comes to the tribological contact, when we had most metal-metal contact. So this is a comparison of the behavior of reference oil versus T600. And as we can see, the blue line, T600, it performs perfectly over this period of time. While for the reference oil, we see after just a few minutes, the friction starts to grow, although it dives a little at the end of the process. Lithium grease is the same behavior as well as lithium complex grease. It's amazing for T600 that regardless if you use it as a lubricant or as a part of the major part of grease, we get such a nice result. So if we combine it with 4-ball result that I showed earlier in one of the slides, then we can really feel that the numbers that we are discussing are solid. So now we are moving to the measurement of the wear on the ball as well as the volume that has been removed from the surface of the plate. And here is very obvious that this size is bigger than this size, and the color indicates more wear here compared with here. So when we measure, we see that on the ball we have 18% less wear, and from the plate we have almost 80% less wear. So for the greases, lithium grease, we see less difference, and if you remember from 4-ball, we had very close to each other. The wear score was, if I remember correctly, it was 0.61 and 0.51, something like that. So we see that the wear here is very close when it comes to the lithium grease. However, when it comes to the plate, we are about 20% less when we use T600 as a base oil. For lithium complex greases, the same. Here we see the gap, in fact, much bigger. We talk about on the ball, the wear on the ball is minus 35%, and the wear on the plate is 81%. So all this percentage here and there is really indicating that we have something solid. We could contribute to reduce the consumption of lithium in lithium grease and lithium complex grease. We could show that the performance based on the characteristics, typical characteristics for the greases are excellent, good to excellent. And here we see that the tribological behavior are also excellent, although we haven't used any additives. Now I'm close to my last slides. This is what I'm burning for, linking the usage of the component in the formulation to the productivity, to the production. Very often based on my knowledge, my experience, and lots of friends that I have within this business, I realize that we are often good to excellent formulators. And we have also good to excellent manufacturers. But seldom we talk about the impact of selecting a raw material on the productivity, on the production side. So here my statement is that it is possible to make more grease with this good quality, with the same quality, by selecting the right oil. So, increased productivity index, what is this? This means if you make two greases which fulfill same specification, but with different type of oil, if you divide one yield to the other, what the index or the number that you get at the end of the calculation should be above 1. If it is less than 1, you lose money in the production, in the process, because it's an indication of the productivity. If it is higher than 1, good for you. You have not only chosen the right oil to fulfill the specification and fix the supply and other parameters that you have on your table, but also at the same time you have contributed to increase or utilize the maximum potential of your process. It is dependent on two parameters, viscosity direct relationship between the viscosity and inverse annealing point. So it means that if you increase the viscosity, you can increase your productivity. If you increase, if you have a good oil with good solvency, so the annealing point is low. So it means that the inverse will be a high number. But if you have an oil like T600, which has both good viscosity and good solvency, you get multiple effect. This multiple effect could be demonstrated by this picture, for instance. This is the typical line for manufacturing of grease, regardless if it is pressurized or open kettle, so-called open kettle, atmospheric kettle. So what you do is that this is your bottleneck. This is the most expensive part in your system, in your manufacturing process. It is jacketed. You have to go up to about 200 degrees C. And you cannot have as much soap as you want. So it is limited maybe to 20% of soap. So let's say, just assuming that you have 20% soap in this stage, 50% of total oil that you are going to have in your finished product is loaded here. And then what you do during the cooling stage is that you add 50% more in order to end up with 10% soap, right? Now, if we use, for instance, an oil with high solvency and high viscosity, like T600 here, since you need less soap here, and also the viscosity contributes to a high solvency, so high viscosity, high consistency of the grease. So you can add here more oil and ending up with more grease. So simple as it is. So what you do is that if you look at the process, you have a thickening step and you have a thinning step. What you do is that by having a powerful product here, powerful oil, you can add more oil during the thinning step and ending up with more grease. You don't need to invest in a new cooking kettle, for instance. You don't need to have more manpower. And it is very easy to verify. Whether the IPI will be 10% more or 30% more, it is remained to be answered by manufacturers, depending on the capability and the type of oil that they use. But to me, this is, here we have money that has been ignored and not really identified. So we have also done some exercise. For instance, what happens if we blend T600 with, for instance, T110, which is a naphthenic oil with 100 centistone. So very easy, since they have same solvency, so we can end up with different viscosities. And as we increase the viscosity, we lose pour point, but at the same time we gain flash point. But the annealing point, which is indicating the solvency of the product, remained constant. So in summary, I went through based on what we have done. So the strength of using high viscous naphthenic oils, both reference oil as well as T600, for three different types of greases demonstrated. These strengths are at least part of the solution to the situation of lithium grease and lithium market that we are facing, and this challenge is going to be combined with the rationalization of the base oil industry, which is another story. T600 outperformed reference oil in all aspects. The only deviation was on the low temperature mobility. T600 improves both viscosity and solvency of other oils, so very easily can be combined and is compatible with other type of oils, group 1, 2, 3, of course. And last but not least, I went through increased productivity index, which I really, really sincerely believe is important for the manufacturers. And by those, obrigado, and thank you very much.